lecture 44, but we basically continue from where we left off so that the properties can be built upon. So one thing that you will notice is that if I initialize with the all zero state, then I will get stuck in the all zero state. I will not come out of it. So in the shift register sequences, if you think of x1, x2, x3, x4 as a state, x1, x2, x3, x4 as a form of a state of the state machine, then it will cycle through. The maximum length shift register sequence basically says that this interconnection is such that the state will not repeat until you have gone 2 to the power of m minus 1. Why is it m minus 1? Because the all zero state is excluded, because once you go into the all zero state you will not come out of it. So all zero state is excluded, all zero state is not present in our in this system. All zero state is excluded, except for that all the other 4 states represented by 4 bits. So that will be 2 to the power of 4 minus the all zero state are present in this shift register sequence. So please do check that you do cycle through all of those. There are some interesting properties that will emerge that are used by CDMA systems, and that I would like to just quickly run through those properties. Okay. One of the important points to note is that if you look at the, by the way, many times when we prove the properties of PN sequences, we will use the following mapping. 0 gets mapped to a 1 and a 1 gets mapped to a minus 1. So basically the 1 minus 2 bi is the mapping that is used, and therefore we get this. So just so that since I told you that you could do both mappings possible, but most of the time when we talk about the properties of PN sequences, we are using this mapping. Okay. So take a quick look at this length 15, which is going to repeat afterwards. So the number of zeros 1, 2, 3, 4, 5, 6, 7. The number of ones is 8. And this is a universal property. Again, PN sequences should have equal number of zeros and ones, that only then. So basically this is called the balance property. So the number of zeros and ones is almost the same, and in all these m sequences, there will be 2 to the power of m by 2 minus 1 ones, so many zeros that the number of ones is 1 more, and 2 to the power of m by 2 ones. Okay, so and you will get, so that will give you 2 to the power of m minus 1 total length of the sequence. So basically it maintains that balance across all primitive polynomials. If you generate, you will find that this is a property. And of course the length of the sequence has to be 2 to the power of m minus 1, otherwise it's no longer a maximal length shift register sequence, and all the properties I'm talking about do not apply if you don't have that type of a sequence. Okay, another important property for which we need to refer to the sequence, so let me just write it down: 0 0 0 1 0 0 1 1 0 1 0 1 1 1 1. This is the length sequence of length 15, and basically we define something called a run. Run is a sequence of successive digits that are the same. So a run represents a sequence of the same bits. So if it's a 0, if you get 0 0, that's a run of length 2. 0 0 0 is a run of length 3 of the same bit. Okay. So number of runs of length 1. Can you just tell me? This is a run of length 1. This is 1. This is 1. This is 1. Okay. So number of runs of length is equal to 4. Runs of length 2. Runs of length 2 is this combination, so that's equal to 2, and you'll find. So basically this property is called the run length property. Run length property. and the run length property says the following. It says that the number of runs of length 1. Again, these are very interesting, that these properties. So this is approximately 1/2 of the total number of runs. Total number of runs. So take all the possible runs of length 1, 2, 3, all of those, and then the number of runs of length 2 is approximately 1/4 of the total. Number of runs of length 3 is 1/8 of the total, and so on. So basically, the likelihood of runs of longer length become increasingly less probable. Okay, so again, if it's a truly random sequence, getting a long string of ones should be very unlikely, and that's sort of reflected in the PN sequences as well. Now, this run length property is not something that we look at much, but the property that we do look at very, very closely is this balance property, because that comes to play in a number of things that we are interested in. Okay, so let me just give you one very interesting, very simple calculation. I would like you to do the following correlation. Okay, the correlation is between the basic sequence and a sequence that is right shifted by 1. So the basic sequence is 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1. Did I get that correct? One more 1 is there. Okay. So now do a circular shift. So the 1 comes to this type, then it comes 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1. Okay. Now correlation, when correlation, for that you will need to do plus minus 1, then you can multiply and add. But if you want to do it in the binary field itself, you can do exclusive OR. Effectively, you will get the same thing, and that's a property that I'm sure you are familiar with from GF2 operations. But do the exclusive OR. So basically, you have to find out where all the bits agree and where they disagree. So disagree means the output will be 1, agree means the output will be 0. So A, disagree, disagree, agree, disagree, agree, disagree, 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 agree, agree, agree. Okay. So number of agrees, 1, 2, 3, 4, 5, 6, 7. Number of agrees 7, which means the number of disagrees must be equal to 8. Disagrees equal to 8. Basically, if I add them up, right? So each of the agrees corresponds to a 0. So that will basically contribute to a plus 1. So 1 into 7. These disagrees will correspond to 1. They will correspond to minus 1 into 8. If I add, I will get a minus 1 as the total. So this correlation value of minus 1 is a very, very interesting property when we do this circular shifts. Okay. Now there is the reason it is so interesting is the following. These M sequences have a property called the shift property. Again, if you have studied them before, I'll just quickly mention them. So if I have a sequence, so basically take the original sequence, if I call that as B, and let me call another sequence B subscript K. That means I have done K circular shifts of that. Okay. So basically, if I now do B of n, that is each of those bits, exclusive OR with bk of n. That means it's another sequence which has been right shifted. This will come out to be b subscript L of n, where L is not equal to k. It will come out to be another cyclic shift of the original sequence. So the sequence plus a cyclic shift will give you another cyclic shift. Okay. Now, the fact that what cyclic shift it is does not matter. The fact that it's a closed group, basically you add two of them, you will get an answer that comes from within the group itself. Okay. So, that is an interesting property by itself. So, now if I combine this shift property and this correlation property, then I get a very interesting and a powerful result, which is the takeaway from this discussion. So, basically if I now define a correlation, I am defining a very specific type of correlation, please note the definition. Rx of k is defined as 1 over q summation L is equal to 0 through q minus 1 x of L x star of L minus k modulo q. Modulo q. Modulo q means it is a cyclic shift basically. So, what this says is I have defined my autocorrelation in terms of a sequence with cyclic shifts of itself. So, basically it is a property that correlation typically would be you just slide linearly, but this is a circular type of correlation that we have got. Okay. Now, correlation of a sequence with it shift with itself will give me what? -1. So, this is guaranteed to be -1 over q, -1 over q. Okay. So, basically if k is equal to 0, Rx of 0, you will get 1. So, at 0 lag you get 1, at all other lags you get some small number -1 over q. Now, that reminds you of the property of random sequences. That is exactly what we have been able to achieve. At least from a correlation point of view, these pseudo random sequences actually map to the, but the only thing is I am not doing linear correlation, I am doing a circular correlation, but it is very important for us to know that. And please do look up the basic proof of this correlation property. It relies on the fact that correlation can be written in terms of a, so in other words, if I do this x1 of n, x2 of n, okay. So, if where x1 and x2 are from plus minus 1s, this is the same as 1 minus 2 times s1 of n exclusive or s2 of n, and the relationship is that x1 of n is equal to 1 minus 2 times, is that the right way to, yeah, 1 minus 2 times s1 of n, x2 of n is 1 minus 2 times s2 of n. So, basically s1 and s2 are the binary counterparts, and you map it to +1 -1 using this. This is a you can do exhaustively verify, because there are only 4 combinations possible. You can verify that this is true. If this is true, then you can write this step as 1 over q summation L equal to 0 through q minus 1 minus the sum of 2 sequences. One will be S of n exclusive or S of n, it should be minus k, sorry. This will be S of n minus k modulo q. Okay. Now, this we know is another shifted sequence of the same of the length. So, this will be some S of n minus L modulo q, some other shift S of n minus L modulo q, and basically if I sum any of these sequences, what I will get is -1. So, basically you can prove that in the general case Rx of k is equal to minus 1 over q if k not equal to 0 and Rx of 0 equal to 1. So, that is a general proof or general result. You can verify that, basically construct the proof and verify that. Okay. Now comes the very, very interesting and important results. Okay. First of all, a couple of observations. These are PN sequences, correct? Now, if you knew what the feedback taps were, so question number 1. So, you know the feedback taps that you know the shift register feedback taps are known. Okay. How many outputs should you observe before you can figure out what the feedback taps are? Is the question clear? I have given you the connections. I have given you the shift register connections. Okay, I have given you this connections, but how many outputs should you observe before you can basically say, okay, now I can figure out the rest of the sequence? Okay. Think about that. You let me know the answer. So, how many outputs should I observe? Okay. Outputs should I observe? A more interesting question is, if I do not know the feedback taps not known are not known, in that case how many should I observe? This is a very important question, okay, and the reason for that will become known very, very soon. Okay. Because PN sequences are often used in encryption. So, if you want to crack what the encryption, or basically you must be able to synchronize with the PN sequence, and so you must be able to figure out what the feedback taps are and what are the current state, so that you can then track the sequence. Okay. So, but that's an aside, interesting, just for simple things for you to think about. Now comes the issue of multiple users. Okay. Take the case where m equal to 4. I had a length 15 sequence. Okay. Now, how many other sequences are there which have good properties with this original sequence? All the right shifted versions of it. So, so there is the original sequence plus 14 shifted versions. Am I correct? Shifted versions. Is that correct? Because basically whatever m is, 2 to the power of m minus 2 to the power of m minus 1 is the length of the sequence. So, there is one original, and then there are these circular shifts, okay, all the circular shifted versions. Okay. Shifted versions. So, how many sequences do I have? 2 to the power of m minus 1. 2 to the power of m minus 1 sequences are there. Okay. So, now if I want to have each user have a sequence, I have to give you one sequence, the next person I give one right shifted version of that, and the other next person another right shifted version of that. Okay. Now, in a multipath environment, I am the base station, you are transmitting, let us say 3 of you, you have got one shifted version, original sequence, one shift, 2 shifts. Now, it is a multipath environment. Now, I am receiving the signal, okay. I am receiving bit 1 with the original sequence, bit 2 with one right shifted one, bit 3 with another right shifted one. Okay. Now, I do not know whether these 3 are multipath of yours or are they independent users. I have no way of knowing, because the multipath will look exactly the same. It will look like one shifted version, and I will not find the difference. So, there is a confusion between multipath and multi-user. Okay. So, if users are assigned, if all codes are assigned, I have a problem. Okay. The problem is cannot distinguish between multipath and multi-user signals. it looks, I mean, it looks exactly, cannot distinguish between multipath of user 1, multipath of user versus multi-user signals. Okay. So, what is the option? How can I prevent ambiguity with respect to multipath? You say that, okay, if I can have a multipath delay of 2 units of time, then I cannot assign the immediate 2 shifts. After that, I can assign. Okay, good, very good. I'm glad you're thinking along those lines. That's a correct answer. Now, how severe is that, and is that going to pose a problem? That is what we need to quickly look at, and the best way to do it is through a quick example. Okay, so a quick example of that. So, the wideband CDMA system, I'll already start to introduce these numbers so that you will become familiar with it before we actually come to that. Wideband CDMA system uses a spreading factor, or the spread bandwidth is 3.84 mega chips per second. MCPS. So, that means the bandwidth of the signal will be around 5 megahertz. So, this uses approximately 5 megahertz bandwidth. Okay. So, basically you can see that, but the basic signals that is transmitting maybe 9.6 kilobits per second. So, it is using spreading to get the bandwidth that we are interested in. Okay. So, this basically means that the chip duration is 260.4 nanoseconds, 1 by the chip rate. Okay, 1 by 3.84 megachips per second gives me 260 nanoseconds. So, supposing if you remember our channel models, one of the common channel models typically says that it can have up to 5 microseconds when you are using in outdoor. So, let us say that the maximum delay spread in an outdoor channel, delay spread is approximately 5 microseconds. Okay? So, 5 microseconds divided by TC comes out to be 19.2. So, how many shifts can you not use? If I use 1, I cannot use 19 of the others. Then, so the number of codes then become very, very limited, right? So, this is not going to work, because though pseudo-noise sequences have got these beautiful properties, particularly these shift register sequences, this multipath business, because all the codes are shifted versions of each other, and there is a fundamental limitation in terms of this. So, this is in a multipath environment, particularly when there is these chips are of short duration, I am going to have a very, very severe limitation. So, the number of available sequences is going to go down very drastically, because of I have to avoid assigning those. So, not available, usable. Available is full, 2 to the power of m minus 1s are available, but I cannot use them because I want to do that. Okay? So, then somebody says, well, how did you generate the PN sequence? You took a primitive polynomial. Take the other primitive polynomials. What's the problem? Just there are GF2 says there are other primitive polynomials. Okay, that's a good argument. So, basically take sequences from different M sequences. In other words, option 2 is take from or assign sequences from different M sequences. That means from different primitive polynomials or from different shift register sequences. Okay? So, basically this means from different generator polynomials, and here again you will find that there are not too many generator polynomials. If you want to take order 4, there is only 2 available. So, basically there are not too many available, but let's look at the. So, this is m 2 to the power of m minus 1, that is what we have. How many possible different M sequences? Number of possible different M sequences. That means how many different polynomials exist for that. Okay? But the most important thing is what is their worst case correlation. maximum over all k r x y of k, that is cross correlation, because I need to be able to suppress the multi-user interference, divided by r x of 0. It is a normalized cross correlation that we are asked to measure. Okay. We started off with the example of 4. If I did not have this multipath constraint, I would have had 15 very good sequences. But if you take the wideband CDMA case, I am out of luck, because the other 14 cannot be used, because the multipath delay is 19 chips. So then I say, okay, how many other M sequences are there? Only one other polynomial. So the total number of fourth order primitive polynomials is 2. That is not the biggest factor. The cross correlation actually is quite high, 0.6. What would it have been had it been an M sequence of this? It would have been 1 over 15. 1 over 15. So it would have been, so basically had you used from within the M sequence, within this one family, it would have been 0.067. Okay, so it would have been actually a very good system, but this stupid multipath ruined the whole thing. Okay. Now again, m equal to 4 is only a simple example, but typically you have to go for something much larger. So let us look at 12. 4095 sequences are available, cyclic shifts. The number of possible sequences, primitive polynomials, is 144. But if you are unlucky and you pick the wrong combination, you can have a cross correlation which is as high as 0.34, when in fact the M sequence would have given you 2.4 into 10 power minus 4. It would have given you 1 over 4095. Okay. So basically you can see that M sequences are going to be restrictive in their use. Then you may ask the question, why do you spend so much time studying M sequences if you are going to say that at the end of the day they are not useful? No, actually they are useful. They form the backbone of the CDMA systems, and we will now, when we look at it, you will see how. So let us go back and say, okay, now what are the spreading sequences that we can use for the CDMA systems? So here is where CDMA 2000 we take as our case study. CDMA 2000 says I am going to use Walsh-Hadamard sequences. Okay, and I believe we have already studied Walsh-Hadamard sequences in a different context. So basically the first sequence, or the first level sequence, is 1 1 1 minus 1. The next level sequence basically will be H1 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 minus H1. Okay, these are all matrices. Okay, so basically that becomes a 4 by 4 matrix, and then you can do. So in general, the matrix at the nth level is the matrix at the n minus 1th level, Hn minus 1, Hn minus 1 minus Hn minus 1. Okay, so basically it goes a power of 2. So this, at this stage you will have 2 power n orthogonal sequences of length 2 power n. You can verify. H2 will be 4 sequences of length 4, and Hn will be 2 power n and they are orthogonal, and again their properties are very, very useful. Okay, so please generate a 4 by 4 matrix. 1 1 1 1 1 minus 1 1 minus 1 1 1 1 minus 1 minus 1 minus 1 minus 1 1. Okay, these are perfectly orthogonal sequences. Okay, so what we look at the cross correlation at if you look at these two sequences, just as a illustrative example, they are orthogonal, but you shift them by 1, what do you get? if you shift them by 1, basically do a circular shift, you get perfect correlation. You get correlation of 4. I mean, this is worse than different M sequences, no? Because basically it gave you as if you are doing perfectly aligned. So this is also going to be a problem, because multipath is going to be present, and if it so happens that my data comes with a delay of 1, I am going to see a very high correlation with some other user's data. Now here comes the key element. Now what is it that can make this look different, make this sequence, make a particular sequence look different from a shifted version? What is it that can make it look like a shifted version? Now this problem had to actually be solved for a CDMA system. So basically a CDMA system, we will go back to drawing our hexagons. Okay. Base stations at the center, let us just look at this. Now all these base stations are using the same frequency. Users in each of these cells must be able to estimate the channel, okay, and it should not depend on which cell I am in, because the method of channel estimation must be the same. So the way the system was designed, again a very brilliant method, was that you transmit all zeros, all the base stations. Then you say, okay, how am I going to figure out, was it base station 1, 2 or 3? 1, 2 or 3. They said we will exclusive OR this with a M sequence, okay, for base station 1, for base station 1, for base station 1, BS1, and will exclusive OR this with a shifted M sequence, shifted, or the same M sequence, shifted one for base station 2, and so on and so forth. So it is the same all 0 sequence, but each of these M sequences are shifted versions of each other. Now remember I told you that we cannot have, because of multipath you cannot have some are omitted. So they said not a problem, what we will do is we will take a very long sequence, 2 to the power of 15, that means primitive polynomial of order 15. So you will get a sequence of length 2 to the power of 15 minus 1. Okay. So basically this will be the sequence that will scramble the all 0 sequence, and these sequences that each of these base stations are using are going to be shifted by 64 chips. Why 64 chips? That means there is no way you can confuse multipaths. If you are using the sequence, the next person is using shifted by 64. So your multipath will be long gone before I can never confuse your sequence with that. So that is where the M sequences have come into play. So what it did was you could transmit the same all 0 sequence by all base stations, and the property of M sequences are such that they have beautiful correlation properties. All you have to do is make sure that the length is long enough and you omit the things that get confused by multipath. So shifted by 64. So all base stations in CDMA 2000 are going to be using the M sequences to scramble, so that I can differentiate between that. Now the same principle is also used to take these Walsh-Hadamard codes, and also what you do is you scramble it with an M sequence. Okay. Now the M sequence is a pseudo-random sequence. If I shift by 1, that is multipath, that is original sequence shifted by 1 is multipath. Original sequence multiplying with the next set of M chips, that is user 2. So I will never confuse user 2 signal with the multipath component, because the M sequence is going to scramble them differently. Okay. So this particular code scrambled by the M sequence will never be confused with the other code shifted by 1, because the M sequences are multiplying them are different. So the M sequences, rather than being the spreading sequences, have become the scrambling sequences, the basis on which you will differentiate between multi-user and multi-path. So again, very important element. I hope you see the benefit. So very quickly, let us construct the CDMA 2000 system and make sure that we are comfortable with the. So the first channel that we have to design is what is called the pilot channel. This is the channel that will be used for doing the channel estimation. So pilot channels has only zeros, no information. It's only used for channel estimation, so that you can do coherent detection. And what are the things that you are trying to estimate? You are trying to estimate the multipath. You have to estimate with the delays. So multipath, you are estimating the delays, all of that. That's the pilot channel. That's number one. The second one that we have to transmit is something called the sync channel. Sync channel is actually the one that tells you the operator, the base station information, all of that. So this is what is carried by the sync channel, system ID. You have to read it and understand. It tells you how to synchronize, because the data is scrambled, is using the M sequences. So a lot of system information has to be transmitted so that you can then synchronize with that. It also tells you what is the PN sequence. Okay, basically it will tell you what is the PN sequence information it will provide, so that you can synchronize to that. So it has a lot of information that you need in order to be able to connect to the. This is the same as what we called in GSM the control channel. Basically the control information is what is called as sync channel here. Okay. The third information that has to be sent for a CDMA system, as in all cellular systems, is a paging channel. A paging channel, this is where the registration occurs. It has the paging, it has messages to individual mobiles. So basically communication between the base station and the mobiles, but it is not user data. It is basically control information that is going forth. And finally, number 4 is traffic channels. Traffic channels. Okay. So this is user data. Now remember we said that we are using Walsh-Hadamard codes. Basically we use 64 length Walsh-Hadamard codes. So basically we are looking at H6. H6. So that means I will have spreading codes starting from W0, Walsh code 0 to Walsh 63. Those are the codes that are available to me. So what is used on the pilot channel is W0. That happens to be the all 0 code. Okay, so basically there is no information going on. It's all zeros. The only thing is there will be a scrambling sequence that will make it look like a random sequence, and that's what is used for channel estimation. The sync channel is by convention uses W32 +1 -1 +1 -1. That's the alternating sequence. The paging channel is usually assigned W1 spreading code. So this can be anything except W0, W1 and W32. So I have a total of 64, so I can have anything up to 61 codes. So in other words, I can support up to 61 users, and the system, from practical experience, you will never run out of codes, because the cells are designed such that the number of codes are more than sufficient. Okay, so now at a top level, it seems like, okay, this is reasonable. Let's now take a closer look at this particular system. So how is this system constructed? Again, this is where you will appreciate the complexity of the system in order to build something that is practical. Okay, so this is how it is built. So the pilot channel is all zeros. Okay, on it you superimpose the W0, which is also all zeros. And then you apply some gain to it. You may want to boost the pilot channel so you can have good channel estimation. So that is your first one. That is your, I'm sorry, this is This is pilot channel. So this is pilot. The second one is sync channel. Sync channel, this is how it's transmitted in CDMA 2000. The sync channel, it does not have very high data rate. It's 1.2 kbps is the information rate. So you take this information rate, do a rate 1/2 convolution code, R is equal to 1/2, K equal to 9 convolutional code. This is a convolutional code. So rate 1/2, so 1.2 will become 2.4 kbps, correct, at the output. Now we are going to repeat the data. So 2x repeat, this becomes 4.8 kbps. So basically each bit or block of bits you repeat, this becomes 4.8 kilobits per second. Then this data is interleaved, and this information. Now we have to apply the spreading code W32. So each bit will get multiplied by a 64 length sequence, but the actual way it is done is you repeat that 64 length sequence 4 times. W32, 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 you repeat it length 4 times. So basically it looks like a 64 times 4 times sequence, or you can think of it as the following. You can think of it as a sequence that is coming at 19.2 kbps, this 4.8 multiplied by 4 multiplied by 64 length sequence, this will come out to be 1.2288 mega chips per second. That is the bandwidth of CDMA 2000. So W0 is at 1.2288 mega chips per second. So this channel is also at 1.2288 MCPS. Okay. So you will find that all of our channels have to be at the same rate, because all of them are part of the same CDMA signal. Okay. So this is straightforward. Let's now move on to the paging channel. You will see a lot of similarities with this, but some differences as well. Paging channel. Now notice that the sync channel, there is no what you call scrambling. Everybody should be able to read it without much difficulty. So it is information is present in a straightforward manner. Paging channel, 4.8 kilobits per second is the basic rate. It can be 9.6 kilobits per second if it is a large cell, depends on how it is. So this again is convolutionally coded. Rate 1/2 convolutional coded, rate is equal to 1/2 constraint length 9. So 4.8 will become 9.6 kilobits per second. You do a 2x repeat, then it will become 19.2 kilobits per second. So 2x repeat, then you interleave, this is at 19.2 kbps. Okay. Of course, at this point, we are going to multiply with the spreading factor, which is the W1. But before you get to that, there is some operation that is done, and again, this is where the CDMA complexity actually starts to kick in. The system is designed such that only users who are connected to their system can actually access the information. Just by listening to this information, you cannot decode. And how did they make that happen? So they designed something called a long PN code. Long PN code. Now long PN code is a length 42 shift register sequence. I mean, that takes 37 days before it repeats itself, at 1.228 megachips per second. It takes a long time to repeat, because that's the length of the sequence. And they take this long PN sequence, they scramble it based on a user specific mask. So not only is the sequence itself, the original sequence itself is hard enough, it's scrambled first, and you decimate or downsample by a factor, you downsample by a factor of 64, you will get something at 19.2 kilobits per second. So this information is going to be exclusive ORed with a sequence First of all is a long PN sequence. It has been further modified, downsampled, and then that is going to scramble your data. Okay. Now this one is going to be spread by W1, and then this is also going to come at 1.2288 megachips per second. That's paging channel. Okay. Now what happens if you want to do traffic? That's the last one. Okay. So traffic is along the same lines as the paging channel. Again, just for completeness, let's write it down so that if ever you are reading the CDMA 2000, you will actually appreciate the information. So traffic channel is at 9. By the way, if it was 9.6 kilobits per second, this 2x is not there, because then it will already be with rate 1.5 convolution code, it will be at 19.2. So traffic channels are at 9.6 kilobits per second. Convolution code rate 1.5, all of them are the same things. Already at 19.2 kilobits per second, the data is interleaved. Okay. Now a very interesting, some very unique thing is happening. Okay. What it does is this data is also scrambled. This data is also scrambled by. Oh, I'm sorry, I did make a mistake. This is not user specific. It's a mask. Basically, it is for all the users in the system. The same long PN sequence, 2 to the power of 42. Here the scrambling of that, the subsequent scrambling of that is by a user specific mask. Okay. Then you downsample by a factor of 64. That will make it 19.2 kilobits per second. Okay. Now use this information to scramble this, and you're going to do something very, very interesting. You're going to puncture some data out of your sequence. User data is already put into a very complicated format. Now from that sequence, you're going to pull out 800 bits per second. It's at 19.2 kilobits per second. So you puncture some number of bits at 800 bits per second. Now which bits you puncture is going to be told by this sequence. Okay. So basically this long PN sequence, user specific mask, downsampled by 64, is going to scramble it, and it's also going to tell you some random combination of bit positions to pull out. And this information is then spread by, well, you should, if you're doing it in the binary, it's a plus sign. Okay, basically it's a spreading sequence, Wj. This can be any of the spreading sequences that are done, and of course this is the output. Now what is it that you punctured in and what did you insert? This is what we call as the power control bits. What is the base station trying to do? This is the base station is what is sending to you. It is sending to you constantly 800 times a second. It sends you either a 0 or a 1. Okay. If it sends you a 0, you have to go down by 1 dB. 0 implies increment by 1 dB. 1 means decrement by 1 dB. Okay. So supposing you are transmitting at the correct power level. Let us say you are at a correct power level. So and the base station is happy with where you are. What it will tell you is it will keep telling you +1, -0, 1, 0, 1. So which means you will be oscillating around this point. Now suddenly you came off very close to the base station. So the base station say, hey, wait a minute, I don't want you transmitting at this power level. I need you to cut the power level here. So what will happen? But it cannot do the jump suddenly. So it will start sending you -1s, it will start sending you zeros, 1s. So each time you will decrease. Once you reach the new power level, again you will oscillate. Okay. Now how many times a second is the base station controlling your power? 800 times a second. Okay. Why is it so important in a CDMA system to control the power so many times and to control it so tightly? Near far problem. Because if you transmit with too much power, then somebody else's signal will get affected because these sequences are not perfectly orthogonal. And so at the end of the day, in order for me to achieve the full capacity. So Actually to build a receiver for this is highly non-trivial, because first you have to know the long sequence, you have to know the user specific mask, the general mask is there is power control, and if you puncture the wrong place, what will you do? You will take user data and you will decode it as power control, and which will be totally wrong. So, so you must actually, this where you have punctured to insert the power control bits has to be precisely known to the mobile. I have to extract the correct bits, and now add all of these things together. Okay, now I have the base station signal, I have paging that is going in. Then there is the before paging, even the pilot is going in. There is the sync channel that is going in, and then I have a whole bunch of users. So it could be user 1 to user n, all their signals, basically using different codes, all of them punctured, power control, all of that is and I come out with a data sequence, and the same data is sent on both the I and the Q branches. This is the I and the Q branch. This is further scrambled by another PN sequence, PNI and PNQ, and then basically it goes into an IQ modulator, and then you transmit as a signal. So this is a CDMA 2000 signal. If you have a CDMA phone, it's doing this all the time. Okay, basically listening to the pilot channel, estimating the channel, looking at the sync, and then getting the information from the paging channel, and then going to the traffic channels, and then detecting. Now in GSM, all of these were on different time slots. So you basically listen to the signal at different time slots. Whereas here, all the information is coming at the same time. So when you want to detect the traffic signal, you must be able to suppress the other signals, and that is where CDMA comes in. All the other user signals, all the other overhead signals channels are all coming on the same channel, and you are suppressing them and taking out the data that you want. Okay, so that is how a CDMA system is CDMA 2000 system is built. Now I told you CDMA 2000 and wideband CDMA are competitors. So what was the basic difference between the two? In this particular case, CDMA 2000, the data rate that you could support was 9.6 kilobits per second. If you wanted to transmit more data rate, what are the options available to you? You would have to take more codes. You take W3, W4, W5, and they won't interfere with each other, because so you would have to use multiple codes to transmit more higher data rates, right? Straightforward. But if one user says I want 10 codes, then you will run out of codes very soon, right? Because you have only certain limited number. So this CDMA systems are you have to be careful about how. So then they said, well, you know what, this may not work all the time. So how are we going to support users who ask for high data rates? And so wideband CDMA system came up with this brilliant proposition. So they said that, okay, a wideband CDMA system, we will support anywhere from up to 384 kilobits per second. 384 kilobits per second to 2 megabits per second. So again, the bandwidth that is used is a 5 megahertz channel. So therefore, there is room for spreading. But how are we going to support these data rates? So basically, here is the proposition. I have a following scenario. I have user 1, and he's been given a spreading code Q1, and it has to reach 3.84 megachips per second. Remember, all these signals before transmission must be at the same chip rate. So user 1, Q1, and therefore you can conclude what is the rate of user 1. Rate 1 will be 3.84 divided by Q1. Okay, basically that's the rate at which the information is coming in. So now if there is user 2, let me use a different color, user 2, and the user 2 says, no, I don't want R1. I'm not, I don't need such a high data rate. So I want only half the data rate. Now that's a tricky question. Now what do you do with this guy? You can do two things. You can take his data and repeat it twice. Just like remember we repeated, so you get the same data rate and you can apply the same spreading factor, because his rate repeated twice it will give you the other thing that wideband CDMA said is, oh, you know what, I am going to give you Q2 which is 2 times Q1, 2 times Q1. Okay. So here is the challenge that we have, and again I will just tell you the answer and then build on it in the next lecture. So user 1 says I am going to spread my data using a spreading factor Q1. This is Q1, Q1. Now user 2 says my symbol now is going to require 2 Q1. This is equal to Q2. So in the time that user 1 transmits 2 symbols, user 2 transmits only 1 symbol. So basically his spreading is different. Okay. Now the challenge is, how do I preserve orthogonality between, see I can, when it came to sequences of the same length, at least I had some control over it. Now if you tell me I am going to have these spreading factors which are quite large and it is going to vary over a quite wide range, how do I ensure orthogonality? And the brilliant observation is the following. So they said, okay, what spreading codes to use? Walsh-Hadamard. So here is the Walsh-Hadamard tree. 1, when I split it, it becomes 1, 1, 1, minus 1. Remember, that is the basic process of splitting. Splitting this 1, 1, 1, 1, 1, 1, minus 1, minus 1. This one will split as 1, minus 1, 1, minus 1. Second one is 1, minus 1, minus 1, plus 1. So basically the sequence goes as follows. Okay. So now if you were to label these, let me just call this as length 4 code 1, let me call this code 0. This is length 4 code 1, length 4 code 2, and length 4 code 3. Okay. Now length 4 code 2, I am going to expand this further. This will be 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. The lower branch will be 1 minus 1, 1 minus 1, and then the negative of that minus 1, 1, minus 1, 1. Okay. And if you go through the numbering process, this will be code of length 8, and this will be the code number 4, this will be code number 5. Okay. If I want you to just pause for a moment and see if I had given user 1, if I had given user 1 4, 2, code 4, 2, and user 2 code 8, 4, what would be the correlation between the two of them? 100%, because it is exactly the same thing or with a flip. So basically completely it would mess up my things. But the observation is, go to any other branch, the other branches are daughters or basically children of the codes coming from 40, 41 and 43. Because 42 is orthogonal to 40, 41 and 43, it is also orthogonal to any of its children, any of their children. Okay. So the brilliant observation was this: designing these codes of different lengths that have still preserved orthogonality is not a problem. I can do that by using these Walsh-Hadamard codes. I just have to make sure that I do not assign parent and child. I just have to make sure that if I assign one here, I have to take the other codes from other parents. Okay. So it's a very, very interesting way. But what about multipath? Problem. How do you solve multipath problem?
That's it, that's all. So now that's how
wideband CDMA was designed. So you basically took Walsh-Hadamard codes, parent but don't repeat any of the children. Basically, they must all have distinct, have roots that are orthogonal, and on top of that, apply a M sequence which will make it robust to multipath. Okay, that you will not get confused between multipath, and that's how the wideband CDMA system is designed. So again, we'll just spend a little bit more time. I just wanted to make sure that you are confident of the basics, and codes are very important part of it. And once you have a handle on the codes, CDMA systems at the end of the day are very, very interesting systems to work with. Okay, thank you very much. We'll pick it up in tomorrow's class.